Hey, it's Mr. Saltano. This video is going to explain a couple of important gas laws known as Boyle's Law and Charles' Law. But before we get to that, let's go over some of the really important basics. What I really want to encourage in this unit is that rather than trying to memorize these as you see them, just think about how they are in your real life. All of these things that I'm going to be talking about, you've seen in real life. So use your intuition to try to make sense of this rather than just brute force memorizing. So for example, we said how pressure is defined as force divided by an area, but you know intuitively that it's how much force you apply to a certain spot or a certain area, right? Gas pressure is the same thing. It's the force exerted by a gas per surface area on the container wall. So instead of you pressing, it's the gas at this point for the gas pressure. Now we also know intuitively, we've all seen that where you have a deflated ball when you're trying to play, right? We know that in order to get the pressure back, we would add more gas particles. We would inflate it, right? We would add more gas particles. So let's take that and try to connect why that happens, though. The reason why that happens is because gas pressure is caused by how hard and how frequent the gas particles are colliding with the container wall. So for example, in this deflated soccer ball on the left, we can see that there's only so many gas particles, and because there's only so many, they can only impact the walls every so often of the container of the ball. When we inflate it, we have far more gas particles, which means a lot more collisions. They're pressing against the walls a lot more often, and that's causing a greater pressure, essentially, and so the ball feels a lot more firm because of it, because of all those gas particles bouncing around and hitting up against the wall. We also may not know this, but air actually has mass, right? So people tend to think air doesn't have mass, and it is relatively light, but it does have mass. So here's an example. On the right is our deflated basketball, and on the left is our inflated basketball, and the basketball on the left is actually tipping the scale, right? It's got more mass than the one on the right, and that's because air has mass, and also because the inflated ball has more air particles in it. Okay, so that's what we call a direct relationship, where one variable goes up, the other variable also goes up. But let's talk more about that. So here on the left we're saying that there's actually 9 gas particles in this container, just to simplify it. I'm sure there'd actually be a lot more in real life because they're tiny. And the pressure gauge is reading 100 kPa, or 100 kilopascals of pressure. Now, if you were to count the particles later on, there's actually 18 in this second picture. So the number of particles has been doubled, it's been multiplied by 2. And the pressure in kPa has also doubled as well. So not only is this a direct relationship where they're both doing the same thing, but this is actually a directly proportional relationship. Meaning that when one gets multiplied by 2, the other also gets multiplied by 2. We double the number of particles, we also double the pressure. If we were to triple the number of particles, we would triple the pressure. Or if we were to half the number of particles divided by 2, the pressure would be cut in half as well. And notice how this has to be, so this is defined as when a gas is pumped into a closed, rigid container, the pressure increases proportional to the number of particles added. So this only works in a rigid container. If this container was flexible or like a balloon or something, it wouldn't work because the balloon would be getting bigger and the pressure wouldn't be able to mount as much as in a closed, rigid container. So some of these things have very specific rules. We also didn't change any other variables. We only changed number of particles and pressure changed. So all of these laws I'm about to talk about involve changing only a couple of variables, and you have to leave everything else constant, otherwise it doesn't work. So let's take a look at another one then. So now what we're going to establish is the relationship that is actually Boyle's Law. So we haven't gotten to Boyle's Law just yet. Boyle's Law describes the relationship between volume and pressure. So what do a volume of a gas and pressure have to do with each other? How they affect each other? Here in our simulation we can see that there's 1.55 atm of pressure at the moment, right? That's generated by the gas particles that are present. Their collisions against the wall are creating a pressure, right? We're trying to determine the relationship between volume and pressure only. So that means I can't change the number of particles if I want to test this relationship, and I can't change the temperature in Kelvin either because I'm just testing 2 variables. Otherwise it's going to muck things up and we won't be able to really tell what's happening. So what I'm about to do is I'm about to take this volume of 500 liters and I'm about to double it to 1,000 liters. So in other words, my volume is going to be twice as big, right? I'm increasing the volume, I'm doubling it. Now try to think about what you think will happen to pressure. Remember that pressure is caused by how often the particles collide with the container wall. Do you think that they will collide more often with a bigger volume of a container and cause more pressure? Or do you think they will collide less often with the container wall and create less pressure? Let's find out what happens. I'm only changing the volume. Let's see what happens to the pressure gauge. So we can see what happened. You can tell actually as the volume went up, the volume increased, our pressure went down. So that is an inverse relationship where two variables do the opposite of each other. Not only that actually, but this is actually an inversely proportional relationship. Now, why is that? Well, we used to be at 1.55 pressure. When I multiplied the volume by 2, the pressure got divided by 2. So they did the opposite, but also the factor of how much they changed was actually the same. When one was multiplied by 2, the other was divided by 2, and that's where the proportionality comes in. So they're inversely proportional because one goes up, the other goes down for the inverse part, and the proportional part is because they changed by the same factor, even though they went in opposite directions. So that is how Boyle's law works. So here is another visualization of that. Just show you one more example where we have a volume of 1 liter, increase the volume to 2 liters, and then the pressure went from 100 kPa to only 50 kPa. So the volume got doubled, the pressure got divided by 2, just like we just saw. So that is the relationship, and changing volume is another way to change pressure. Half the volume doubles the pressure and vice versa. So that's how that works. And again, this is only going to work if we have a container that can actually, like this wouldn't work in a rigid container because our volume has to be able to change in order for this to work. Okay, so that's for Boyle's law. The other important thing is to examine the graph of Boyle's law. Here it is on the right. This is what the graph of any inverse or opposite relationship looks like. By the way, there's some formulas here. We don't have to use those this year. We're just focusing on the relationship. So we're not going to be plugging anything into formulas. But so this graph is what the relationship looks like. So we can see how it makes sense. This curve is what you're always going to see. But we can see that as pressure, which is on the y-axis, as the pressure goes down, right? The volume, which is on the x-axis, goes more to the right. Whenever something's on the x-axis, we know to the right means it's increasing. So as we go down on the y-axis, as a decrease, we're going to the right on the x-axis, which is an increase. So as pressure goes down, volume is going up. The opposite also happens, right? As the volume goes down, as we move to the left, the pressure is going up. So this is where this curve comes from. This is what an inverse relationship looks like, this graph, essentially. It's that curve. Okay, so let's look at our last relationship of the video. Okay, so now we're back at our simulation. What we're going to look at now is the relationship between temperature and volume. And so remember, these laws only work if you only change a couple of variables at a time. If I'm going to look at just the relationship between temperature and volume, I have to make sure pressure doesn't change, and I also can't change the number of particles while I do this, because then that's going to impact everything. So these laws only work when you're describing two variables. We saw Boyle's law was just volume and pressure. This last one we're looking at is Charles's law, which is the relationship between volume and temperature. So what do you think will happen when I heat up this container? Do you think that it will get bigger? Do you think that the container will shrink down? Do you think this plunger will shrink down more? Or think about what you think will happen. I'm going to heat it now. We'll see what happens. So as I heated it, and I kept the pressure constant and the number of particles constant, that's the only way this works. As I heated it, the volume increased, right? So in other words, the heat went up and the volume also went up. So this is what kind of relationship? This is a direct relationship. And we're also going to look at this as a directly proportional relationship. So let's check that out. So here is that relationship we were looking at between volume and temperature. Here's our original gas, and then as the gas is heated, it actually moves this little part inside the glass tubing, causing the gas to take up more volume. And again, this is only because the pressure is held constant. So we notice here, as we heat up the gas in this balloon, the balloon's getting bigger, and that's how the pressure is actually staying constant, because the balloon's getting bigger. If our balloon couldn't get bigger, then our pressure would also increase, right? So this only works because the balloon can get bigger. And then if we were to cool it down, the balloon gets smaller again. So it's a direct relationship. But it's directly proportional as well, is how Charles' law works. So for example, here's our original container. It's at 1 liter and 300 Kelvin for temperature, and the pressure is 100 kPa. For the second container we're looking at, the pressure is still 100 kPa. We're not changing that part. But we're doubling the temperature from 300 Kelvin to 600 Kelvin. And what that does is that causes the volume to also double to 2 liters. So this is a directly proportional relationship. They both go in the same direction, both go up together, both go down together. But also they do it in proportion. So they get multiplied both together or divided both together by the same factor. One important note, this only works if you use the Kelvin scale. It's because Kelvin is directly related to kinetic energy. The other scales are not. So this only works in Kelvin, something very important to know. And even though we don't have to know the formulas, I kept this one here just to emphasize. Remember in math when you do proportions? That's what this is showing. Volume 1 over volume 2 is to volume 1 is to volume 2. Volume 1 is to temperature 1, as volume 2 is to temperature 2. So it's just a proportion. The last thing we want to look at is the graph of this. So this is what a graph of a directly proportional relationship looks like. Now it's a straight line. They both go up together, and they both go down together. That's opposite of the curve that we saw in Boyle's law. And this is actually how we came up with absolute zero, which we'll talk about more in class. So that's it for Charles' law and Boyle's law. Thanks for watching. Remember, chemistry is everywhere.